Okay, so internal resistance, define the internal resistance. So you can write the definition like it is the electrical resistance inside the battery. Simple. Okay. Or you can say that it is the opposition offered to electron inside the battery. Internal resistance is the opposition offered to electron inside the battery.
What about lost volts?
Lost volt is the multiplication of internal resistance times current. Small r, yes. Small r.
Oh.
Yeah, this is the internal resistance. So lost volt, which that voltage will lost inside the battery.
And the terminal PD is V equals IR.
That is potential. You can say that determination is it is the potential difference across the cell. And in explanation, you can write this that if my current is equal to 0, then my EMF will be equal to what?
EMF will equal 0.
EMF will be equal to 0. Yesterday I explained this in detail.
No, sorry. Wait. It will be IR.
Yes, it will be equal to IR. Actually, your EMF that is equal to I small r plus terminal potential difference. So if your current is equal to 0, then your EMF that will be equal to terminal potential difference. Okay. Got it?
No, but terminal PD will not be present because if current is 0, then V
there
equals...
will be a current. There will be a potential difference. If there is no current, then still there will be a potential. There will be a potential.
Really?
Yeah, there will be when you buy a cell. Okay, so on cell, they wrote that 1.5 volt. So there is no current, but still they write there 1.5 volt because if you connect the terminal of voltmeter across this cell, then voltmeter will give you 1.5 volt.
But then how come if there's a terminal PD, why is there no internal PD, internal resistance?
Okay.
Oh, because there's no current, so therefore no opposition to that.
So
I get it.
Okay, wait. Water will flow in which direction? If this is the river, and this is the water, okay? Water will flow in which direction?
There, like that.
Yeah, toward left side, okay? Toward left side. If there is no water, then still this slope will be present. So you can think that this water is the electron. If there is no electron, then still this difference will be present over here.
Oh.
Okay. And if there is water, then still this will.
Yeah, I get it.
Okay. So that is okay. So if your current is equal to 0, then your EMF will also be equal to potential difference. And that is the terminal potential. Then there will be no loss inside the internal resistance. Maybe in MCQs this come that when your current is equal to 0, so is there any loss inside the internal resistance? Then your answer will be no.
Yeah. Did you send me the notes from today? I don't know. I don't think yesterday's notes. I don't think you saved it, right?
Okay, I saved this note. Okay.
Okay, you can send it later. It's fine.
Next question. Outline an experiment that could be performed to investigate the internal resistance of a power supply. Include detail of the apparatus used, the measurement taken, and any data analysis performed. Okay, so this is a bit difficult questions. Is there anything in your mind related to this question?
Wait, I want to clarify question 1.
Okay.
PD. Okay, fine. Are you okay?
Yes, I am okay, but I am waiting for you. That is this clarify question number 1 part A?
Oh yeah.
You said that I want to clarify this question, so that's why I wait.
Oh, sorry. I thought you were angry.
Okay. So read this question.
Okay, outline experiment that could be performed to investigate the internal resistance of a power supply. Okay, you put like this, and then put a resistor.
What about?
We can put a lamp to limit the current.
Yes, you will put alarm. Is that alarm or that lamp?
It's a lamp.
It's a lamp, yes.
And then.
And what's about the internal resistance?
Oh yeah, what do we do?
Um,
Oh my gosh, you just explained it. When I equals 0,
then
then EMF equals V.
yes, then
So you can put the variable resistor to maximum so that current will be 0, so that EMF can be calculated. And then you can put variable resistor to minimum so current can flow through, and then the lost volts can also be calculated. And then you subtract. So it will be IR equals EMF minus V.
okay. So when your current is equal to 0, so you calculate that, and your EMF is equal to so, and your current will be equal to 0 when your outside resistor is equal to infinity.
Yeah.
But if you have a huge battery, then you will put lots of resistance in series. If you have lots of small resistor, okay.
Yeah.
Yeah, that will cover up all your laboratory, okay. Okay, so you will get your voltage will be equal to EMF, and if the current is not equal to 0, then okay, so then you then explain it further. IR is equal to EMF minus C. What is mean by this?
Lost volts will equal to EMF.
And how you will find the lost volt?
Wait, this is wrong. I'm doing it wrong.
Yeah, you are doing it wrong.
Clear it.
Okay.
You can't find the EMF.
Wait, I will try. Okay, this is my EMF, and this is the internal resistor. And here, let's say according to you, I will put variable resistor.
Yeah.
Okay, so this is my EMF, this is internal resistor, and this is okay. Okay, so in lab there will be all these apparatus will be present there. Okay, in lab, and in lab I will also have ammeter, so I will connect ammeter over here, and I will also a voltmeter. So connecting voltmeter over here is impossible. Is it possible to connect voltmeter over here? If it is possible,
Yeah,
then if it is possible, then it will be too much easy for me because I will get E value, EMF value. But what do you think?
yeah.
Is it possible to connect voltmeter across these 2 points?
No, because the voltmeter is not that precise. I don't know. Why is it not possible?
It's not possible to connect voltmeter across over here because if you have a battery, okay, if you have a battery, then this battery has its own internal resistance, okay.
Yeah.
Okay, so finding internal resistance inside this battery is impossible, and you will get voltage only across this terminal. So you can connect voltmeter across over here.
Oh, but that will give you the terminal PD.
Yes, that will give you terminal PD because connecting voltmeter across here is impossible because it is impossible because we only in circuit we connect it like this, that we said that the EMF is this and internal resistance is this, because this.
Why don't you connect it here?
Yeah, you can connect it over here. It is same as connecting like over here.
It will
Because
give the same value.
yeah, it
right?
will give the same value because connecting this needle over here will give the same value. Here will give the same value. Here will give the same value because this is the same path. Connecting over here will give the same value. Connecting over here will give the same value. Similarly, this terminal connecting across any point on any point on this line will give you the same value. So you can connect it over here or you can connect it over here.
Yeah. Okay, I get it.
Okay, so I have voltmeter, I use voltmeter, I use ammeter. Okay.
So,
Okay, so okay, I will have a term. Okay, equation is equal to IR plus terminal voltage. Okay, I will have this value because I will find it through through voltmeter. I will have this value. E and R is unknown. E
you
and
can
R.
put it Y equals MX plus C.
Okay, wait. Let's draw a graph for this.
I don't know what I'm saying.
So let's say I am taking voltage on y-axis. Okay.
Yeah.
Okay. So this will be my current, and this will be my voltage. Okay.
Oh, this will be y-intercept.
So when your current is equal to 0, then your EMF will be equal to V. So let's say at this point, my EMF is equal to V. Okay. And then if you increase the current, then your terminal voltage will get decreased. And over here, your current, your voltage will be equal to 0, so your current will be equal to E divided by R.
Wait, why don't you put V here? Because this is an independent variable.
Just for simplicity, I put
Okay,
V
fine.
over here. Okay. So you can put V over here and current will be. So you will also get the same curve. Okay. Okay. So
No. Why are you putting E over R here?
sorry. If your voltage is equal to 0, this is the voltage. If this is equal to 0, then your EMF will be equal to IR. Okay. And your I will be equal to E divided by R. So at this point, your I will be equal to E divided by R.
If you put V here, I here, and then you plot it like this will be easy because here it will be IR, and then the gradient will be M, which is the gradient will equal to V.
No,
So we can do.
but in this case, if your current is equal to 0, then your V will be equal to, so V will be equal to, let's say this is equal to E. And when your voltage is equal to 0, then your I will be equal to EMF divided by R. So let's say that point is over here. So you will get a straight line like this. So it will be.
Okay, fine. Yeah, I get it.
Okay, why I draw this straight line over here?
Basically, which is linear proportional, linear relationship. Because V is proportional to current.
Yeah, it's a linear equation. So that's how we draw it. Okay. Okay. So the gradient. Okay. So this, I have EMF and I have current, internal resistor. Okay. And plus voltage. And I connect the variable resistor over here. Okay. So if I change this resistor, then it will change my current.
Yeah.
And your terminal voltage will also get changed. But your battery will remain same. Your E will remain same and your R will also remain same. So you can say that your E, that will remain same. Your current will get changed, I1. Your internal resistor will get same, that will be equal to V1. So at current I1, your terminal voltage will be equal to V1.
I don't understand how you got this. How do you know?
Okay, on this axis, voltage is equal to 0. Terminal voltage is equal to 0.
Yeah.
This voltage is equal to 0. So if this is equal to 0, then your E will be equal to IR. And your I will be equal to E divided by R. So this is the current axis. So the current at this point, let's say at this point, is equal to E divided by R.
Oh.
Okay. So you got this equation?
Yeah, I got it.
Let's say at R1. Okay. Now I am going to change this resistor. Okay. So at R2, EMF is still same because I am using the same battery. Current will get changed because now R is going to be changed. So I2, that should be equal to I2. And internal resistor, that is also same, plus V2. Okay, now subtract equation 1 from 2. So you will get, because we have two equations and two unknown, so it means we can find the unknown. Okay, so you will get 0. That's equal to I1 minus I2 into R plus V1 minus V2. Okay, so your if I bring this part over here, so it will be like your R into I1 minus I2, that will be equal to minus, or you can say that V2 minus V1.
The
Okay.
internal resistance remains constant, right?
Yeah,
Well,
it will, because I am using same battery. I am only changing this resistor.
But even when current or resistance changes, internal resistance remains the same because it's independent of the.
No, in laboratory, I just pick up the battery, okay? Let's say that is 1.5 volt battery. So I am using the same battery. I am just changing the external resistor, capital R.
Yeah, so capital R is not affecting little r, small r.
Yeah, that is not affecting this little r, small r. Yes, that's
why
only affect the current,
Okay, I get it.
and that will also affect the lost volt.
Yeah, but it won't change. It will always remain constant.
But internal resistor will remain constant.
So why are you making it hard for yourself? Look, I have an easier method. If you do E equals IR plus V, then we can do E will also remain constant, right?
Yeah, it will also remain constant. Yes.
Because energy is conserved. So what you can do is you can rearrange this. It will be V equals IR minus E. Then you will get. So then we can put this Y equals. Put Ri here. So M X plus C. So the y-intercept will be the E, and then the M will be the R, and then the X will be the I. So we can compare. This is much easier. Look, do you understand what I was trying to say? I hope you understand.
Okay, so how you so your internal resistor is equal to slope, okay?
Yeah, that's what I'm saying. Yeah.
So you have unknown values.
No, we know the. Oh, wait. If you plot Y as V here and I, it will form like this, right? So this point will be E.
So your slope will be equal to minus R.
So the slope will be E over I, which is R.
Slope will be equal to E over R. E over I.
E over I. Look here. Here.
Yeah. So slope is equal to
R.
Yeah, E over I is equal to R. Okay. That is not E over I. That is V over I. If you are taking I, then that will be equal to V over I.
Oh yeah. Wait. V over I equals R. I don't know. This is the way my teacher taught me. My teacher said this way, but I forgot the exact method. That's why. But this is the method in the AQA. I forgot. I need to look for it. It was something about comparing the.
Actually, my method is also same. My method is also same.
Yeah, your method is the same, but it's just
Wait. I am thinking that how I convert my method to your method. Just give me a minute.
Okay.
Okay. So actually, now here you saw the solution. Okay, and in solution, is there any graph like this?
Okay, the mark scheme says put a power supply in series with variable resistance ammeter, voltmeter across the power supply. Okay, we did that. Second mark, you will have to do change the resistance to change the current. We did that. Third mark is measure voltage and current for each incremental change in resistance. We did that. And then fourth mark is use the equation EMF equals V terminal plus I internal. And then
okay, wait. Okay, so you have only this question, and if you are sitting in exam, you have only this question, and you only know about the circuit. Okay, you don't know about the graph. Okay.
Yeah.
You don't know about the graph. Okay. So first of all, you in lab you will draw the graph. Okay, you will draw this curve. This will be I, and this will be your voltage. Okay. Then you will use voltmeter and you will use ammeter. So if you will increase this resistor, okay, toward the infinity, okay, so your current will get equal to 0. Okay, so when your current is equal to 0, then you will read the voltmeter value. Let's say that voltmeter value is this. Let's say this is equal to 10.
Yeah, so that would be the terminal PD.
Yeah, that will be the terminal PD, and that will be equal to your EMF. Okay. Now you will decrease. You will decrease the resistor. Okay. So when you decrease the resistor, then you will get a current I1. Okay. You will get a current I1, and on that current I1, you will also get a voltage that is V1. Okay. So you will draw that current like this. Here you will get I1, and here you will get V1. Then you will again decrease the resistor. Okay, little bit decrease the resistor. You will get current I2, and that will give you voltmeter value, that is V2. So here you will get, let's say that is like this point you get. So that is I2 and V2. Similarly, you will again decrease the resistor, and finally you will decrease this resistor to 0. Okay. So when you decrease the value of this resistor and equalize it to 0, then your voltmeter will give you 0 value.
Yeah.
Then your current will be equal to E divided by R.
How do you make voltage equal 0? Do you have to turn the power source off?
Yeah, I remove this resistor.
Oh.
Okay. So here I measure the voltage, but that voltage will be equal to 0, and here I will get E divided by R, but E is also unknown and R is also unknown. Here I will get E divided by R.
Yeah.
Okay. Now let's move toward your part. You said that Y will be equal to mx plus C. Okay. So we will compare the Y will be equal to V, that will be equal to I, X is I, small r plus E. Sorry, your EMF is equal to IR plus capital V. No. Your Y in this case is V. That is equal to IR plus, and C is, let's say that is equal to EMF. In this case, Y intercept is equal to EMF, okay?
Yeah.
Okay, but in this case, the EMF is equal to IR plus capital V. So let's say this is minus V, and this is also equal to minus EMF. Sorry, this is minus R. If this is minus R, then you will also get this equation. So it means,
Wait. Yeah. So minus R equals M.
so it means your gradient is equal to minus R.
Yeah.
So take any two values, okay? This is known, voltmeter, this value is known.
Yeah, just put a triangle. It's easy. But then.
Okay, this value is known, okay? And on this value you will have I2, and this value is also known. So your gradient is equal to V2 minus V1 divided by I2 minus I1. So you can
just
find
write M equals minus R.
Yeah, so you can find I from this your V1 is known, which you took from voltmeter. This is known, and this is known. This is known, and this is known. So you can find the slope because it's a straight line. So find slope over here.
What's the use? How is this useful?
Because internal resistor is, we are going to find the internal resistor, okay? And my slope is equal to internal resistor.
Yeah.
And slope is equal to change in Y value divided by change in current X value. And change in Y value is given to me. And I find it that using the voltmeter. Change in Y value is Y2 minus Y1, and change in current is I2 minus I1.
Yeah.
So your V1 is this, and I1 is this. Your V2 is this, and I2 is.
I know that. That's easy.
Yeah, but this value will be positive. This will give you positive answer result, and this will give you negative result. Because
yeah, I know. You times it by -1. That's easy.
Yeah. So your minus, let's say -4, and then is equal to minus R. So minus R. So your internal resistor will be equal to 4. So you can find your internal resistor through this method.
What's the significance of this?
What? There is no
Yeah.
significance of this. This just give you the final value that at which point it will cross x this current axis.
Okay. So at this point, this is the time. This is a V, right? At this point, it's V.
Actually, through this method, you will get R value. Okay, now you have R value. Okay, hello.
Yeah, I'm listening.
Now you have R value. Okay, so and let's say the current value at this point is 10. Yeah, 20. Okay, so your E by R is equal to 20. So you can find E from this X intercept.
Or you could just do the y-intercept. Y-intercept is also EMF.
Yeah, you can that your Y. Yeah, but for that you will increase this resistor equal to infinity, and practically that is impossible. But there will be also some sort of error. Hopefully, there will be also some sort of error if you take this value, because your R is equal to, it is impossible. Practically, it is impossible to make this infinity. There will also some sort of error.
Yeah.
Okay, next. If you have any question,
Finally.
yeah.
No, I get it. Thank you.
Okay, read this question.
Oh my gosh. Okay. Jeremy is provided with 2 cells each. Oh, I'm gonna. It's so confusing. 6 volts, internal resistance 0.4. Any further?
So for single cell, the terminal voltage will be equal to,
It will be
for single cell.
oh, it will just be 6 volts.
Yeah, that will be equal to 6 volt. Two cell connected in parallel. Okay, and
Wait.
what about the current?
Current here will be 6 divided by 0.4, which is
6 divided by 0.4?
yeah.
Think about it.
Wait, sorry. Anybody can. Sorry, no. 6 divided by 10 will be the.
That is 0.6.
So it will be 0.6 amps.
No.
Sorry, wait. Let me just use the equation. Why am I being lazy? E equals I R plus R. So E, which is 6 volts, divided by 10 plus 0.4 equals I. Therefore, I equals 6 divided by 10.0, 10.4. I equals 0.58 amps.
Yes, that is good as 0.58 amps.
Okay, next question. 2 cells connected in parallel. So 1 over RT equals 1 over 10. 1 over 1 over 0.4 plus 1 over 0.4.
Good, yes.
But the 10 ohm resistor will be in parallel as well, right? That's 1 over 10.
No. No, that will not be in parallel. Draw the circuit diagram so you will get that. It will be in parallel or not.
Oh, yeah, you're right.
Okay, so 0.4 times 0.4 divided by 0.8.
So it will be 1 divided by 5, which is 0.2 ohms. Or
Yeah, 1 divided by 5.
Then 0.2 plus 10 equals 10.2 ohms. So I equals 6 volts divided by 10.2, which is 0.59. No, I'm doing it wrong. Wait, do this again.
There is 0.588. 0.588 is the final answer.
It will be like this, isn't it? But
No,
total.
no, it will not be like this.
It's connected in parallel.
You are making a series connection. Wait, I will do it. Leave it. This is your one cell, and this is the internal resistor of one cell. This is your another cell, and this is the internal resistor of another cell. And over here, you are connecting the standard resistor. This is equal to 10, this is equal to 0.4, this is equal to 0.4. This voltage is 6, this voltage is 6, this will be also equal to 6. Okay, so your current is equal to V divided by R. V is equal to 6 divided by R. You need to find the equivalent resistor, that is equal to 0.2. Now, if this is equal to 0.2, then 0.2 is in series with 10. So that's equal to 10.2.
Yeah, I did that. I did 6 divided by 10.2.
Yeah, so that's equal to 0.588.
Yeah, I got that.
So that is the right answer.
But then when I look at the mark scheme, it's saying 1.16.
That will be for series.
Oh, I think they made a mistake. Okay, fine.
Wait, let's find it for here. So in series,
They put a mistake. For series, they put 1.12, and sorry, for parallel they put 1.12, and for series they put 0.58.
Okay, so your resistor, your voltage will be equal to. In this case, your voltage will be equal to.
It will be 12 volts.
Good. 12 volt divided by.
EMF equals 12 volts. Total R plus 2R will equals to 10 plus 10.8. So it will be 12 divided by 10.8.
And that is equal to 1.111.
Equals 1.11.
So that is the right answer. Okay. Next
But the
question.
mark scheme says 1.16. I think they made a mistake.
No, that's equal to 1.11. Your mocks did a mistake.
Yeah, they did a mistake.
Okay, give an example of when low and when high internal resistor might be desirable. Okay.
I should know this because you explained this so many times. When resistance infinity.
Small, use small. This is internal resistor. Use small R.
When R infinity.
Also remember the lamp. So hopefully you will get an idea. Hands from.
Okay, I'll keep that in mind. When internal resistance is infinity, it limits the current.
Yes, it will limit the current. Yes, it will keep your device safe in the safe zone. Like.
Can I say protect the battery /
Protect battery?
Yeah.
Okay, so no, how it will protect battery?
By preventing short circuit.
Yeah, by preventing short circuit. Okay, good. Yes, by preventing short circuit. Because if this is your EMF and this resistor is too much, okay? And let's say you have a very, you can say that very weak device. You can say that
because
small.
Yeah. For example, a variable resistor with zero resistance. Zero.
No, let's say you are using LED over here, okay? You are using LED, okay? And this is 12 volt battery, big volt battery, like the battery of the car, okay, vehicle. So this battery will destroy this LED. LED is very small, okay? This voltage will destroy this LED. So if this internal resistor is high, then it will guard this LED, okay?
Yeah, because if resistance.
Yeah. So this Huge internal resistor will be beneficial for this small LED.
Yeah, passive component.
Yeah, that is the passive component. So huge voltage will drop. Let's say 9 volt will drop over here. Okay, so only 3 volt will appear across this.
Is it called passive component?
Yeah, this is passive component. This is the active component.
Okay, and if resistance is very low, then less energy loss.
Yeah, then that battery will be your ideal battery. And everyone want this. Everyone want this. That my internal resistance will be equal to 0.
Lamp will be brighter.
Yeah, that will be brighter, but that will also destroy your lamp because the voltage is too much. That is 12 volt. 12 volt battery is a huge battery.
Yeah.
And if you use LED, so that is it have a very small resistance. So very small voltage will drop across this. So high resistance will be beneficial for this lamp. Okay. So you can give this example, but this is only 2 marks. So you can say write this. Less energy will lost if your internal resistance is high, and it will limit the current. Okay, that will be enough for 2 marks. Next. Okay, this is a potential divider.
What?
Read this. Okay, so first question. Leave that. Okay, first question. Define electrical work. Define electrical work in terms of.
Oh, but the other question looks so interesting.
Which question?
The one that we just passed in the other paper.
Yeah, we will do that question tomorrow, inshallah.
Oh my gosh, what am I doing? Okay. Oh yeah, equals IV. Wait. No.
Now use ohm law. V is equal to IR. Good. You got 2 marks. Next part.
The PD across. Oh my god. The PD across 5 ohm resistor is measured as 6 volt over power. It will be equals 5 squared over 6.
That's equal to 5 square over 6.
R squared over V.
That's equal to 5 square over V. V is 6.
Equals 150 watts.
No. Resistor is given to you, and the formula relation between power, voltage, and resistor is equal to.
Oh, V squared over R.
Yeah, V square over R. So that's equal to 36
squared over 5.
Yeah, so 36 square.
7.2.
Yeah, 7.2. Good. Next. Oh, sorry.
Oh my gosh, what happened?
Actually, I didn't save some of my. Okay, leave it.
It's fine. You don't need to save this. This is useless.
Okay, 450. Good. Okay, so 4.6 times 2.2 divided by 4500.
Yeah.
No.
Charge equals current over time.
You are doing lots of silly mistakes, and this will.
Sorry. Oh my god. How did I do that? It will be 2.2 times 4,500.
Yeah, 4,500. Yes.
This current is defined as the number of charges passing a point per second.
Next question.
So the answer will be 4,540 joules. Oh no.
Okay, you need to find the relation between work and resistor.
Okay, fine, here.
Resistor.
Wait. Yeah, put W here, put Q here, then put straight line.
You need to find the relation. Okay, you need to draw the graph between work done.
Sorry. Yeah, you're right. Okay, wait.
Okay, this is the last part, okay?
Yeah. I don't know. Wait, I'm doing it wrong.
Okay, so your work is equal to VQ and your Q is equal to IT.
Yeah.
VI and your I is equal to V by R times T. V squared divided by R, yes. So your work is inversely proportional to, because potential difference is same constant.
But what about T? T is not constant.
At a given point in time T, so time T is also constant. That will be equal to, let's say, 9 seconds or anything.
Oh,
Yeah. So
you're right.
so yeah, so it will have an inverse relation. Okay.
Will it be a straight line or a curved line? It
I
will be
think
straight.
yeah, it will be straight.
Because otherwise, it's not. If it's R square, then it will be curved. It's R. Yeah,
Then that
it will
should
be
be.
straight.
If your x is equal to infinity, then your y will be equal to 0. Yes, that should be okay. If there is any square, then your graph will be like this. Okay, so okay, this is the end of the class because
Yeah.
only 20
Okay,
minutes left.
Oh my gosh. Okay, have yourself retake there. See you tomorrow.
Okay, okay. See you then.